My name's Heather McClarty and I work at the ORE Catapult, and I'm going to be hosting the webinar today. So without further ado, we'll have a look at today's agenda. So I'm going to be giving you an introduction to the speakers we've got today and a bit about the Catapult. I'll then be handing over to my colleague Charlotte, who's going to set the scene of the cable industry and touch on what the reaction project is. I'll then hand over to Synaptec, who will give you a bit of an outline of their company and technology and details of the leave and mouse trial that we've done and the data that we've been able to get from that. There will finally be a Q&A session, so please do comment any questions or comments in the chat box function, and we'll get to that at the end. A couple other little housekeeping things. This webinar is being recorded. If there's any major issues with that, please get in touch. But the slides and the recording of this webinar will be made available at the end. So without further ado, we'll get stuck in. So like I mentioned, I'm Heather McClarty and I'm one of the speakers on today's webinar, and I'm one of the project managers at ORE Catapult. My colleague Charlotte Strang-Moran is the technical lead from Catapult on this Innovate UK funded project, and she's an electrical engineer at ORE Catapult. We've also got Neil Gordon, David Young and Stephen Blair speaking on the webinar from Synaptec, and later on for the Q&A we've got Philip Orr and Tom Morley on the panel available for questions. So a bit to set the scene about the Catapult before we get stuck into the details of the project. Hopefully many of you listening will be aware of who we are at Catapult. We're one of the 9 catapults that are located across the UK that are designed to transform the UK's capability for innovation. We work very closely with Innovate UK, and today we'll be going into details of the Reaction project that is one of our many Innovate UK funded projects. Our mission at ORE Catapult is to accelerate the creation and growth of UK companies in the offshore renewable energy industry. So we work really closely with SMEs like Synaptic, and this is a prime example of one of our projects that we work on. Hopefully that set the scene a bit about what we do at Catapult, and I'll now hand over to Charlotte, who's going to give you a bit of a background to the cables industry and get into the Reaction project. So over to you, Charlotte.
Thanks, Heather. Good afternoon, everyone, and thank you for joining us today for this fantastic webinar. As you can see from this great turnout, cable reliability is a hot topic in the industry. I will be providing a brief overview of why Synaptic's technology is of importance to the sector, before handing it over to the Synaptic team to go into more detail. Subsea cable failure is an issue which is detrimental to both export and inter-array cables. From ORE Catapult's recorded operational failures, 17% of offshore wind farms in the UK have reportedly suffered from inter-array cable failure and 33% from export cable failure. The possibility of more incidents occurring or have happened but have been unreported is very possible, as there is limited access to cable failure data. Although subsea cables make up a very small percentage of the cost of installation, they make up a very high percentage of offshore wind insurance claims. The graph on the bottom right of your screen is from a report produced by the insurance company G-Cube. It shows insurance claims only up to 2015, but it demonstrates the increase there has been in claims and the increase in costs. As more offshore wind farms are installed around the world, there has been an increase in the number of insurance claims. This is costing the industry. Repairs are expensive, and insurance claims are only just the tip of the iceberg of how much subsea cables are affected from various faults. Many faults because of harsh environments these cables are installed in, and other due to the length to which these cable designs and materials can withstand the environments in which the cables are operating in. As technology adapts and offshore wind develops, subsea cables are also required to acclimatise and become more reliable. Cable monitoring systems are used to proactively determine when the system needs attention for replacement or repairs through preventive maintenance, or through integration with the control system. Another way to use condition monitoring is when the cable has already been damaged and the event is under investigation. But by utilising cable monitoring technology in proactive ways, however, certain faults can be avoided. This being said, there are a variety of ways in which the cable can endure faults and therefore eventually lead to failure. During the operational stage of a site, cables can be threatened by environmental influences, misdesigned systems, or defects occurring in the cable before operation. The cable can be affected by environmental influences such as changes in the water movement resulting in scour or seabed movement. The cable moving can cause damage over time. Defects can occur from storage, transport, installation, or manufacturing that can also cause damage over time. Or if, for example, the design, production, or installation of the cable has perhaps been executed below the required standards, this can cause problems later on as well. Cable protection systems can fail, leaving the cable damaged or at risk of being damaged, and partial discharge can affect the cable system at various points. Weak points are high-risk areas of the system, like joints or cable terminations. As these failures occur to inter-array cables, depending on the wind farm's fault detection methods and the redundancy a site has in place, a full string could lose generation, or the string's downtime is lengthened due to procedures for identifying which is the damaged cable. There are a multitude of reasons why cables fail, and there are various condition monitoring systems out there to detect various aspects like heat, partial discharge, acoustics, or strain. Synaptec's technology is looking to use differential protection to monitor the cables, and temperature sensors to monitor heat anomalies in the terminations. Synaptic system was introduced at the Levermouth turbine through the project Renewable Energy Array Cable and Termination Instrumentation Using Optical Sensor Networks, aka the Reaction Project. The aim and objective of this project was to determine fault detection in array cable strings and to detect anomalies and faults in the terminations, an area of the system that, if left unmonitored, faults can be undetected until they amount to a failure and generation is lost. At Levermouth turbine, we have had reaction installed and measurements are being recorded. This has led to further investigation into the system's potential and how Synaptec's technology can benefit more than just monitoring the cable's fatigue, but monitoring as well the power quality.
Thanks, Charlotte. Sorry, I was on mute there. Hopefully that set the scene for everybody quite well. We're going to hand over to Synaptec now. So Neil, if you can request control.
Okay.
Thanks, Neil.
All right, thanks, Heather. So I'm just going to give everyone here a brief introduction to the company, to our unique sensor technology, and really how we apply that in the offshore wind sector. So Synaptec as a company is built upon our unique optical sensing technology. This allows us to deploy unprecedented numbers of completely passive electromechanical sensors throughout a power system. And for the operator, this is designed to give them a unified and holistic electrical and mechanical visibility and control of their systems with unprecedented speed, range, and price when compared to conventional methods. Since the company was founded in 2015, we've had this proven in mission-critical terrestrial transmission applications and shown that it's uniquely able to perform protection and automated condition monitoring of medium and high voltage assets. So since 2015, as you can see in this timeline along the bottom here, we've worked in the UK with Scottish Power and SSE, in Europe with the likes of Statnet, and now with the help of the Catapult and the Reaction project, we're doing our first pilot project in the offshore wind sector. And we've already had, off the back of that, our first deployment at scale in the offshore sector planned for later this year. So the technology that we have, we refer to as distributed electromechanical sensing, or DES. So what we do is we deploy passive sensor networks leveraging the existing single mode fiber in that network. to provide distributed measurement of electrical and mechanical parameters. What this means is if an operator has single mode fibre present in the network, we can splice in passive point sensors for any of these parameters shown here, so voltage, current, strain, vibration, and temperature. If one of these point sensors is electrical, it will interface with the secondary side of a standard primary converter, so a current or a voltage transformer. And we can provide that primary connection, or we can retrofit to the secondary of an existing device. And those comply fully with the IEC standards of the industry. If it's a mechanical sensor, then that simply mounts onto the desired substrate to be measured for strain, vibration, or temperature. And that uses standard, existing, and safe installation techniques that would be familiar to any installer in the offshore industry. As I've said, we leverage the existing standard single mode fibre in that power network. So in the subsea sector, obviously that's the bundle of many fibres that you have in the cable itself. And with just one of these fibres, we can measure up to, or we can deploy up to 50 sensors for these parameters shown on the screen. So that voltage, current, strain, vibration, and temperature. And those are simply spliced in at the measurement location. And because they're completely passive, there's no requirement for any auxiliary equipment like power supplies, active telecoms, or or housings or things like that, or GPS access. So that makes it much more lightweight, it takes up much less space, and is generally faster and simpler to install than conventional methods would be. The measurements from all of these sensors, regardless of the measurand, are encoded in optical wavelength, an analog optical measurement in fibre. So that means that they're immune to electromagnetic interference, which means we can distribute them over a very long distance without any degradation in quality, and they're inherently secure to hacking or other cybersecurity issues. So essentially what this means is that this technology forms a platform technology for instrumentation of power networks and can be installed really anywhere there is access to the existing fibre network. So the sensors can be deployed over a very large area, and then at one end we have this single powered device, which is the interrogator. So this will measure up to 50 sensors per fibre over a distance of up to 100 kilometers nominal distance from the interrogator to the final sensor in that array. And as I've said, this is the only powered and time synchronized device in the system, and typically those will be available anyway in the substation. In terms of outputs from this device, we would have standard measurement outputs to the process bus, so digital sampled values, and also measurements going to our own software system, which we'll talk about a bit later on, which will do more advanced analytics on the power quality and the condition monitoring side. So for offshore wind, we have this platform technology with the interrogator and all these different measurements that we can produce or that we can gather in with that system. But for the offshore side, we're focusing first of all on synchronous and continuous measurement of current and temperature, in particular in the turbine transition piece. And that's to be used for improved O&M response to faults and for improved asset management throughout an array. So if we just have a look at how we might deploy in a typical offshore array, we could imagine installing current and temperature in the transition piece of every turbine on each string. And that would be at the cable termination points inside those transition pieces. Again, they're completely passive, so there's no active electronics required at those locations, reducing the size of that instrumentation and the amount of work that has to go into installing it. If we put current sensors, first of all, if we look at those, current sensors in each of those transition pieces at the termination point would enable completely reliable and discriminative differential protection of the inter-array cables. And if there's already a protection system there protecting that array, then instead it would give you immediate faulted cable identification to improve the O&M response to a fault. If we have discrete temperature monitoring of termination points, then this can be used to monitor trends in temperature and watch out for things like overheating due to ohmic heating of those connectors. And we know from conversations with operators that in some cases, those will be very common points of failure just because that's where manual intervention comes in during the installation. It's also important to note that while a lot of operators will have distributed temperature sensing installed on these systems, typically the sensing fibre that is used for DTS will not measure the termination point. It will come out of the cable and go into the splice box at that point. So it can be very valuable to have, even if DTS is there already, to have a discrete independent monitor of the temperature of that particular asset. So uniquely, because we have all this data coming to a central point at this interrogator, it means all of a sudden we have access to this high quality synchronized point on wave data from every single in that array. So that allows us to then look at the things that Charlotte was talking about power quality indicators. And in particular, it means we can have live power quality indicators from every single turbine in the array. So we're no longer looking at the sum of all the power quality that's measured at the offshore substation necessarily, but actually a discriminative view of what's going on in every single turbine. And the combination of the current and the temperature then allows us to start looking at trend analysis and correlations to think about predictive maintenance and planning O&M responses before a fault occurs. So that's a very, very quick overview of what we do. I should say as well that I've focused here on cable instrumentation or inter-array cable instrumentation, but that's equally applicable to array cables as well, to export cables as well, because the system is exactly the same. But in this project, we were focusing on array cables. So now I'm going to pass over to my colleague David Young, who's going to tell you about the actual installation at Leavenmouth and what was involved in that process. Okay, David?
Hello there, everyone. I'm just waiting for control. Okay. Oops, something's gone wrong there. Hello there. My name is David Young. I'm systems engineer at Synaptec. I'm going to go into more detail on the retrofitting process on the Leavenmouth turbine itself. To jump right in, this is a rough overview of the installation we had. On the onshore side in the substation, we installed the interrogator, which is the main measurement unit, which is doing all the processing, publishing data, and communicating with all other devices in the substation. This is connected to our sensors via a single optical cable. So the first sensors are 3 photonic current sensors also installed in the onshore substation to measure currents at one end of the export cable. These are then connected through an optical fiber to another set of current sensors in the turbine, which then enables us to measure both ends of the export cable and allows protection of this cable. Also installed in the turbine are 4 photonic current temperature sensors to measure temperature of the termination points there. So that all these sensors are connected via one single mode fiber to the interrogator, which takes the measurement. Now to go into a bit more detail of each of these elements. First of all, we have the interrogator. This comes in a standard 19-inch rack to be installed in the substation in a cubicle. That needs obviously be powered. It needs a power supply. It needs a standard single mode telecoms fiber to connect to these sensors. Ethernet connections are required as well. These are to publish our data and measurements. These are published either as the measurements as IEC 61950 sample values, or we can also publish strip signals if we have a protection scheme running, and these are published as goose signals. Further, we require GPS time synchronization of the system, and that is done via industry standards such as PTP or PPS. The current sensors have been retrofitted, as I said, in the substation, onshore, and in the turbine itself. 3 sensors, one per phase, have been installed. These are industry standard CTs connected to our unique passive optical measurement devices, which connect to the secondary of these CTs. The CTs installed here were split core, which enabled a really fast installation and easy retrofitting. At this point here, we don't require any power supply or active communication systems because these sensors are inherently passive. The only connection that's required here is single mode telecoms fiber to the interrogator, and then a second set fiber that leads on to the next sensor in the chain. And this connection can be easily done via local splice boxes. Obviously, the process is very much the same for onshore or offshore installations in a turbine or substation. Next in the line, we've installed temperature sensors to monitor overheating of the cable terminations you can see here. So we've installed 3 sensors on these cable terminations, and then an additional 4th sensor to measure ambient temperature. These sensors can be retrofitted quite easily, either using cable ties, thermally conductive epoxy, or screws, depending on the sensor type or the surface you want to mount to. And again, these sensors are passive, these temperature sensors, so no power is required here. All we require is connection to the interrogator or other sensors in the line via optical telecoms fiber, which makes the whole installation process straightforward and quite easy. And that already summarizes the installation. So what we've done was to retrofit the interrogator, 6 current sensors and 4 temperature sensors, as well as commissioning of the system within just 1 day. The retrofitting itself was performed by OMM personnel on site using standard procedures for CT installation and optical telecom fiber splicing and connectorization. No additional training was required to install our technology here. And the commissioning on site was done by Synaptic engineers. And that was all that had to be done to install the system. And my colleague, Stephen Blair, is going to take you through the next slides about data analysis.
Okay, thanks, David. Okay, good afternoon, everybody. So my name is Stephen Blair, and I'm the Head of Power Systems Technologies at Synaptec. So I'm going to build on what Neil and David have explained about mainly about the hardware platform, and expand on what applications this opens up, particularly in terms of visualization and data analytics. So just to introduce this, this slide kind of shows our architecture for sort of building on the hardware platform and to ensure that we get the best kind of use, the full use out of the kind of new applications that the Synaptic sensor platform opens up. So what's shown in here is that we can acquire data from many different sensor systems potentially, and we can aggregate that all and store the data, visualize it, and perform data analytics on it. So that's mainly what I'm going to talk through today. For the reaction project, this is all built in. It's installed in-site within the, you saw the kind of cabinet that David showed, but we can be flexible about how this is deployed, so we can do all the computation and data storage in the cloud, and it can support, you know, completely private systems if that's needed by any of the system operators. So I thought it'd be more interesting to kind of show you the system in action rather than describe it through bullet points. So I've got a few kind of screen captures here. So this is all pre-recorded material, just to, in case, you know, the wind wasn't blowing right now when we're doing this demo. So this was recorded from a few days ago, and it shows the system in action. So this first screen here shows a geographical view, which allows you to kind of see the context of your system, and if there are multiple systems installed, you can see all of them at the same time, and it lets you zoom into the exact location of where the interrogator system and the individual sensors are installed. So you can see in this case, the Leavenworth wind turbine is just barely offshore there, but it showed that in the geographical view. So it gives you a full view of the wider system, and you can appreciate the level of visibility that the sensing infrastructure can provide. So this next screen gives you a summary of the main electrical and mechanical measurements that are being observed by the system across all locations. In this case, there's just 2 locations. but it would scale to many other locations in different installations. So here you get a summary of all of the measurements for each distinct location. For voltage and current measurements, it automatically calculates synchrophasors and system frequency and other interesting metrics such as THD and imbalance. For temperature sensors, we get the instantaneous and a range of values over a period of time. It also provides some debugging information that's useful during commissioning, or if there are any issues with the telecoms from the system, from the output of the system. This is all about just a convenient single place for all the technical details that engineers might need to use during the operation of the system. So this next screen kind of expands on that, and it shows you the more detailed view for each individual location. So here you can see you've got access to the full detail of the measurement waveform down to the individual samples. So in this case, we're sampling at 4 kilohertz. So we've got that really detailed view. It's kind of seamlessly built into this visualization, which is kind of unusual to have access to that information, especially in real time. It's also automatically performing some power quality measurements. So you can see on the right there, there's a spectrum, harmonic spectrum being calculated just in real time for every voltage and current measurement that's built into the system. So it's a bit like having a built-in network of power quality meters and digital fault recorders all integrated into the same system, but without dedicated units needing to be installed. This is all integrated into the platform. So hopefully this gives you an idea that it makes it quite easy and feasible to perform condition monitoring with very granular data. So we can pick up, very fast transients, electrical transients that you wouldn't normally see in a typical SCADA system. So, for example, electrical arcing, we see the full detail of these kinds of phenomena, and that's something. Electrical arcing is something that could affect the long-term health of assets. So we can also, as well as the instantaneous real-time picture, we can also look at trends over time. So here we can look at different metrics that are aggregated over time, and we can navigate through that and explore the data over different time ranges. And we can go down to the second by second level in this case. We're also merging this with additional data from OREX SCADA system, which is quite well provisioned in this case and has, I think, hundreds of different variables that we can look at here. So this allows us to correlate both electrical and mechanical measurements at the same time, and we can look across those different quantities and see how they correlate, if there are any relationships. So you can build a visual sense of what's going on with the data. And we can also do things like looking at different harmonic signatures over time and see if there are any anomalies. If any of the harmonics change over time, then we could flag that up because it might be due to an underlying mechanical issue or something with the controller of the power electronic converter, or an issue with the filter, or any of the above. So it allows a detailed view that wasn't really possible before because it was kind of the costs of implementing it were excessive. So just to summarize what I've explained, I've shown how the platform can take advantage of the unique properties of the synaptic sensors. So we've got high resolution and we've got a coherent time synchronization. That time synchronization quality alone is really important for me because it removes a major headache when it comes to doing meaningful data analytics in the data, because you can be confident that all the data is taken at the same time effectively, and you don't have to worry about lining up data from different sources because it's inherently time synchronized, usually to a global reference, so you can compare it with other systems too. And what this enables is we think it enables lots of different applications across several different timescales. So we can do really time critical stuff such as protection, we can, the stuff that usually happens on a millisecond basis or sometimes faster, and will usually involve controlling things within a substation. We can build that into the hardware of our system so that it can perform these time critical tasks. We can also build upon that less time critical, but also quite important functions such as oscillating detection of oscillations in the system, which has been quite important in the past year, particularly in the UK, and things like dynamic line rating. It's relatively easy for us to build that in because we've got direct access to current measurements and spot temperature measurements, and additional measurements such as strain and sag are also possible as well, which can be important. And taking the bigger picture, we can also help with long-term objectives, such as maximizing the life of assets and looking for signs of aging that were kind of invisible before because the sensing infrastructure was too costly or impractical. So I just want to quickly just summarize everything that Neil, David, and myself talked about from the Synaptic point of view. So Neil has introduced the sensor platform and talked about the main different characteristics that kind of set this apart from different approaches. I just wanted to stress that this is a completely passive form of infrastructure. So that the sensor infrastructure is minimal compared to conventional technologies, but it still delivers a very granular view of the system. So you don't sacrifice anything by going for this option, even though it is more cost effective. And it has many uses in digital substations or cable monitoring, or in this case, offshore wind monitoring and protection. David also walked you through our kind of a typical installation or an actual installation in the leaf-and-mouth turbine. And so, again, the main point here is while the sensor technology might seem new and unusual, the installation and retrofit process is straightforward. And in many cases, I think it's actually simpler and cheaper than a conventional instrumentation installation. And myself, I've kind of highlighted some of the really interesting and significant opportunities that are available for visualization and data analytics. So we've got new tools to work with to deliver some really powerful tools here. So now I think I'll hand back to Heather, who will start the Q&A, I think.
Yeah, thanks, Stephen. Just request control again. Well, thanks everybody, it's been really interesting. We've had a lot of questions come in, some of them just to the panelists, some to everybody. So what I'm going to do is go through some of them we've got and open up a bit of a discussion. So, just jumping back again. One of the first questions we got is looking at the difference between DTS and DES. I wonder if, Neil, would you be able to describe them a bit and answer that question?
Yes, of course. So I'm sure most people on this call will know that DTS uses the entire fibre core as the measurement medium, which is why it's able to get a continuous measurement of temperature throughout the fibre. That has a particular resolution associated with it of a few meters typically. So one point I made during my section of the presentation was that this fibre will typically bypass the termination point. So while you're getting that continuous measurement of temperature throughout that cable section, you might not see particular items of plant at either end. So how our sensors differ is that they give you a precise, high accuracy point measurement of temperature. The temperature sensors themselves, David showed, and they're approximately 2 centimeters long. So they give you a very targeted measurement of temperature on a particular asset. So this technology shouldn't be seen as a replacement for DTS. Really, I would say they complement each other, because one will give you temperature hotspots or gradients at some fairly high resolution throughout the cable, and we'll have a very high accuracy, high resolution point measurement of temperature at particular locations. Hopefully that helps.
Thanks, Neil, and hopefully that answers your question. The next question we got is, are there plans to integrate online partial discharge sensing at terminations to the Synaptic offering? I wonder if, David, do you want to respond to that one?
I would be happy to respond to that one, Heather. It's Philip Orr here.
You go for it, Phil.
So I kind of answered this in the chat, hopefully, but I will just go over that again. Yes, we recognise that partial discharge is a good advanced indicator of degradation in cables. It's challenging to do that with transducers that are not extremely high bandwidth, and the technology that we use for measuring voltage and current doesn't go to the megahertz range for that. So we're looking at partnerships that bring in those technologies, because we think that the way this industry is going, and please, we would love your feedback on this, we think that what people are looking for is simplified, unified systems that bring together the best-in-class techniques over different technologies to present a holistic view of what's happening on that cable asset. So that's where we want to get to.
Thanks, Phil. The next question we got in, and yeah, these might have been responded to, but we'll just open up for discussion. What level of accuracy would the system given fault or degradation finding along a cable? I don't know, Phil, if you responded to that, or if Neil, if you want to comment.
Yeah, I can jump in on that. So in terms of the system we're describing here, this is giving you differential protection, or equivalently faulted section identification by doing a simple differential current algorithm on that cable that has current sensors on either end. So what that will give you is an immediate indication of the faulted section or the faulted array cable. Beyond that, we also have integrated OTDR functionality into the interrogator unit, which means that after a fault is detected by the differential scheme, we can then, on a timescale of kind of seconds rather than milliseconds for protection, we would be able to tell if there's been a break in the fibre down to a few centimetres in that fibre. Beyond that, we can also think of some more complex electrical methods, like impedance to fault. We had voltage and current on either side of that cable. We could then look at the impedance along that cable to the fault, which would also tell us to a small percentage of the length of that cable. That would give you the accuracy on the location of that fault.
Thanks, Neil. One question came in, are we talking about AC or DC cable systems? Maybe a quick one to go back on.
Yep, so this one is just for AC at the moment. So for current sensing, we offer AC and DC at the moment, and for voltage sensing, sorry, for current sensing, we offer AC at the moment, and for voltage, we can do AC and DC. We're developing DC current, but it's not commercial yet.
Thank you. How was the voltage gradient of the array cable terminations maintained following the installation of the temperature sensors?
So I can probably jump in on that one as well. So that shouldn't be an issue with these temperature sensors, because they're optical fibre, they're dielectric, and they're very small devices. They're made of ceramics and fibre, basically, so there's very little effect at all in there.
Thank you. Hopefully everybody's having similar questions, so it's good to respond to everyone. What is the distance limit for export cables, or can it be used only from one termination? Does that make sense, Neil?
Yeah, in terms of distance limit, we have a kind of nominal distance limit based on attenuation in the fibre, kind of typical losses we expect to see per kilometre of fibre, which we calculate as about 100 kilometres from the interrogator to the final sensor. However, that really depends, you kind of take it on a case-by-case basis, because fibre quality could be better or worse in different installations, new versus retrofit. There's a lot of factors that go into that, and there's a lot of things that we can do to improve that, like amplification and careful design of the sensor network. So there's no one answer to it, but a kind of ballpark figure would be about 100 kilometres. For export cables, you can also consider that we can look in from either end. You know, we could have an interrogator reaching a nominal distance of 100 kilometers from one end and then from the other end as well. So that in total you then cover 200 kilometers. So we can use schemes like that to improve the range quite significantly.
Thank you. We also got a question. Has any lab testing been undertaken relating temperature measurements on the exterior of the cable terminations to the internal temperature and time to failure for the termination?
So in terms of lab testing, we have lots of tests of kind of the accuracy and the lifespan of our sensors, but I guess that's really what this project is going to help us do, is to gather the data that will allow us to examine at a deeper level how the lifetime of that cable is affected by temperature trends of those terminations. And that'll be true as well of the deployment at scale that we're doing later this year, that's designed to find out the answer to that question, really.
We also got a question. Has partial discharge been monitored in either inter-array or export cables?
I can answer this one as well, unless anyone else wants to jump in. So this technology, as Philip mentioned there, doesn't measure partial discharge, of course, because we don't measure at the high kind of megahertz rates that we need to for that. But as Philip said, we're looking at integrating other technologies into our platforms that can do that. So hopefully that's mostly answered by Philip's response already.
Okay, the next question. Has a correlation been undertaken between the current measurements and the temperature measurements?
Again, I think that one is something that we are working on just now as a result of all the data gathering that we're getting out of this project. This is designed to give us access to that wealth of streaming data from an offshore test site to let us examine those in particular. I don't know, Stephen, if you have anything to add to that.
Yeah, but you can definitely see that. You can see the termination temperature, cable termination temperature increasing when the wind turbines at full output power, the full 7 megawatts. So it's quite easy to see that correlation, even just looking at a simple plot of both of those things at the same time. We plan to do kind of more detailed analysis to provide kind of more kind of quantitative stats on that thing.
Can this system replace or complement our TTR system?
Stephen, do you want to jump in on that one?
Yeah, absolutely. Both of those things. So it could be integrated into an existing system if it's there already, or it could provide all the data you'd need to install a new system to do that. So yeah, we see that as one of the very appealing applications of this technology from our customers that we're talking to. So absolutely, we can do that.
Next question. What is the market availability like for photonic current transformers? Are there a range of suitable options for the requirements you have had on projects?
Yes, certainly. I mean, because we work with industry standard CTs, and really our novel technology connects to the secondary side and converts that into an analog optical measurement, we work with standard CT suppliers to the industry who are already well aware of the wealth of requirements for different accuracy classes, for protection and metering classes, different withstand requirements. So really we can cover any voltage and current level that is currently covered by traditional CTs and VTs in the industry.
Comment and question. There's been no mention made of fault finding on cables. Is this system only applicable to separate sensors at terminations, etc.?
So, I mean, in a sense, yes, we are installing this at the cable terminations, but it's about having very fast and discriminative faulted section identification. So you are getting that information very quickly and using that, feeding that back to the O&M response to ensure that an operator is sent out at the earliest possible opportunity after a fault is detected electrically. And then taking a step back, we're also looking at the trend analysis to see can we spot a fault coming based on the temperature and power quality trends, and use that to anticipate a fault and then intervene before that point.
There was mention of full-scale deployment this year. Does that mean that Synaptec are fully market ready?
Yes, yep, that's correct. In the transmission sector, as I mentioned at the start, we've got several commercial projects on the go, and this will be our first commercial project in the offshore industry. So we are definitely ready now.
Would the system be used for full string analysis, or are there issues with this that would require each to have monitoring equipment installed? Would the installation downtime be envisioned to be 1 day or multiple days?
So I think the answer to that is that in this particular installation, we covered 2 installation locations, one in the turbine, one in the onshore side, and the interrogator, and that took a day. So certainly it's going to take longer than a day to instrument a whole string or more of an array, but even then it's going to be significantly quicker than pretty much any other instrumentation technology that's giving the same result, because we don't require, again, all that supporting infrastructure to be there. We don't need power supplies or active telecoms or GPS access at the sensor installation location. It's just snapping on, I mean, if it's a retrofit project, it's snapping on a split core CT, which is very straightforward and safe to do, mounting that and then splicing into the patch box. So you're not talking a significant length of time per sensor, and then that will just scale with the number of installation locations.
I think, just Philip Orr here, I think the start of that question, Heather, kind of related to whether this is a platform for getting data out of each of the cable ends, and perhaps also the turbines situated above them. Yes, that is exactly what this is capable of doing, because of the efficiency of it, having a single interrogator that can see the voltages and currents at each of the cable terminations means that we can look at, for example, the power quality on an individual turbine basis and look for power quality that's deviating from the pack, if you like, to start being proactive about the maintenance both of the machines and also on the cables and their connections, but being very granular. So because we've got the efficiency, we can get away from looking at an aggregate measurement at the end of the array and instead look out along the array at multiple points.
Thanks, Phil. Bit of a broader question. What is the design life for a typical inter-array export cable? Neil, would you be able to step in again?
Well, possibly that might be one for yourself or Charlotte, based on your cable lifetime analysis. I'm not sure.
Are you able to comment?
Hi there. Yep, sorry, could you just repeat that quickly for me, please?
What is the design life for a typical inter-array export cable, if such thing exists?
So the cable tends to be 5 years, 30, but people are looking to want to extend that.
Thanks, Charlotte. Question, can routing drift be detected?
What was that question? Sorry, can you repeat that?
Can routing drift be detected?
I'm afraid I'm not familiar with that. Stephen, would you know what that refers to?
I'm afraid I have no idea what that is either. In the chat, that would be good, and then we can maybe give a better answer.
Yeah, if you want to expand on your question, that would be great.
Yeah, that'd be useful, thank you.
The Synaptic also monitor the damage to cable sheath. So what type of technology is used?
So what we can do, I saw there was a question in the chat, this might be the same one or related, is can you measure the sheath or the earth current in the cable sheath, which is often used as an indicator of a fault in a cable, and yes, we can do that as well. Typically the sheath will be bundled at one end of the cable to earth it. And we can simply install, again, a small split core CT around that point to gather the earth or the earth fault current at that point. And that can be used as a kind of quick and easy identification of fault in a cable.
Thank you, Neil. Next question. Has there been anything interesting that has been seen as an aside to the main aims, such as higher or lower heating in cables terminations than expected?
One for Stephen, perhaps?
Yeah.
So far, we don't know yet. We've only just sort of put together our kind of aggregate database that's collecting our real-time data along with the OREC data collection. So we don't know yet, but that's something we will be investigating, and we'll be able to report on that soon, I hope.
I think it's interesting to note that although we might not have learned what is an advanced warning of some degradation or a correlation that's a bad correlation, we are seeing distinct correlations even on the temperature sensors that are mounted on top of the insulation, which makes them a very easy installation. We're seeing the correlation very clearly between the wind speed, the current being driven, and the temperature of the terminators.
Mm-hmm.
Thanks, Phil. We just got a question in. Can we please explain or show the synaptic voltage measurement sensing solution at the T connectors? What does this look like in practice?
So that's a question about voltage measurement in particular. So in this project, we haven't deployed voltage measurement. Sorry, Philip, did you have something?
Sorry, I thought the question was about temperature.
It's just coming from Michael.
So I'll just finish what I was saying about voltage measurements because it might be of use. In this project, we haven't deployed voltage sensors. That's something that we can do, and indeed we have done in the terrestrial transmission sector. Obviously, that requires a little bit more thought around its installation than just wrapping a CT around an insulated cable, because we have to connect to the primary voltage. So we need a standoff insulator, and we need a connection to that primary voltage at the top of that insulator. But that can certainly be done. It just needs more thought about how you do that inside, for instance, the transition piece. One place where that would, of course, be quite straightforward to do would be in the offshore substation, where you have the bus bar, a standoff insulator, and we connect at that high voltage potential. And then our optical measurement would just go at the secondary of a standard voltage transformer inside that insulator.
Thanks, Neil. And maybe time for one last question. How many fibres are required? Is it just one along the array with numerous sensors spliced into the same fibre?
Yep, that's it. That's exactly correct. So per one fibre that we use, we can deploy 50 sensors. So we daisy chain the sensors along that one fibre. And then if we want to do more than 50 sensors, we would just use a second fibre to add on extra sensors, and it will just multiply up like that.
Okay, since that was a short answer, we'll take the last two. Is there an anticipated timeline for HVDC cable commercial rollouts?
So on that one, I would say we have HVDC voltage sensors that are ready to go. On the current sensing side, though, as I'm sure you'll recognize, because we use current transformers, you can't measure a DC component with those, so we have to investigate other methods of getting DC current. We have several avenues that we're looking at just now, but it's not something that we'll have available this year is DC current sensing, but the voltage and mechanical aspects can all be done right now for DC cables.
I think we'll make this our last question then. Can more detail be given of the OTDR capability of the system that was mentioned as a means of monitoring health of fibres in an export cable?
Yep, happy to. So as you know from this technology, we're using one of those fibres in the export cable or in the array cables as our measurement medium. And from our interrogator, we can also include an OTDR module, which will just it'll kind of flash that fibre whenever we want it to, really, and as OTDR does, it looks at the reflections from particular lossy items down that fibre. So that's really all it does, is it will pick whatever fibre we plug into it, and it will map out the losses down that fibre over, again, this 100-kilometre distance. There is scope to scale that up to look at more than one fibre at once, potentially, but we haven't seen the need yet. And our real application at the moment is as a kind of, for one thing, it will help us with commissioning with the interrogator. It will allow us to very quickly, when we're commissioning everything on site, it will allow us to confirm the optical quality of that network that we have. And then if a fault is detected, it then allows us to get a very quick measurement of the location of that fault based on damage to the fibre at that location. So that's kind of what's planned in at the moment with the interrogator and how we intend to use it. Hopefully
I would maybe just add one thing. So the OTDR obviously is looking at the fibre, and the main use of that from our perspective is to detect damage in the conductor, because they're so closely located that the fibre will likely be damaged by any failure in that cable. The question asks if as a means of monitoring the health of the fibres themselves. So OTDR was originally developed for that purpose, and we can use it for that as well. So if there's surveys to be done of the health of the fibres, that can also be done by the OTDR system.
Yep, good point.
Thanks, Phil and Neil. Well, thanks for a lot of really good, interesting questions. I hope that you've all enjoyed listening to our webinar. We'll close on this slide if it loads. We've also got a podcast that we recorded just yesterday with Synaptic that will be available on the ORE Catapult website. So if you'd like to learn any more, feel free to download and listen to that. A final thanks to all our speakers again and panelists, and a special thanks to Innovate UK for funding this project. I think we will end the webinar there. Thanks for joining everybody in today's webinar.